All right. Our final speaker today is Michael Azarian. He's a research scientist at the Center for Advanced Lifecycle Engineering, or CALS, at the University of Maryland. His primary research interests are detection, prediction, and analysis of failures in electronic components and assemblies. Prior to joining CALS, he spent over a dozen years in the disk drive and fiber optics industries, working at Bookham, W.L. Gore, Senstor, and Philips Research Laboratories. He holds a master's and PhD in material science from Carnegie Mellon University and a bachelor's degree in chemical engineering from Princeton University. Michael.
Thank you very much, Jeff. Welcome, everyone. And I really owe a debt of gratitude to the other panelists this morning who have provided a great foundation for what I intend to talk about. And so perhaps that'll give us an opportunity to spend a little more time in discussion at the end of this, rather than going over all the details. But I'm going to be talking this morning about hardware Trojans and counterfeit microelectronics, focusing on issues of detection and diagnosis. So I'll spend a little bit of time reviewing the varied threats regarding both conventional counterfeits and tampered devices. Go back over some of the topics that we heard about already concerning hardware Trojans. And in particular, I'll talk a little bit about process reliability Trojans. And then, given what we've already heard, it's pretty clear that there are some significant challenges here for the industry in terms of detection and diagnosis of these phenomena. So I'll introduce a little bit of that, and then we'll approach the topic of detection, starting with what the standards that have already been issued offer us in the way of methods for detection, and particularly talking about SAE AS6171. I'll talk also a little bit about side channel methods and related more recently developed techniques, including some work that we've been doing at CALS using deep learning for detection of hardware security threats, and then look a little bit ahead at the future. So by way of introduction, it's a good idea to be aware of the varied types of counterfeits, looking at this kind of broadly, where we see counterfeits as including electronic parts that are essentially a misrepresentation, a deliberate misrepresentation, and can have sources both in reclamation from parts that have been previously used, as well as clones and tampered parts that are deliberately and sometimes maliciously introduced. The topic of tampered parts is really where the hardware security issues that we've been hearing about this morning come into play. These are parts that have been modified in some fashion for malfunction or sabotage, and they're pretty broad category. And we include these within the overall heading of counterfeit parts. I mentioned AS6171 previously. It's a standard that it's been issued by SAE for detection of counterfeit parts. This taxonomy comes out of there, and currently the published version of 6171 does not address tampered parts explicitly, but the committee associated with that standard is actively working on developing methods to address tampered parts in a soon-to-be-released revision and new standards associated with that. So, talking a little bit more about tampered parts. So, looking at it again, fairly broadly. We're kind of treating that as a category of counterfeit part, which has been deliberately altered, and that could be to perform some type of surreptitious function, or in more general sense, to deviate from its expected performance, and that includes hardware Trojans. These parts can be in the form of clones. So these are things that are been created from the ground up to mimic or look like authentic parts, or they can be modifications of an otherwise authentic part. The change that results from that tampering could be programmed to occur upon some trigger conditions. So that's what we think of when we talk about a Trojan. But the trigger conditions, of course, can be fairly complex or very subtle. It could just be a certain amount of usage time, or it could be a condition of the part, or it could be a certain activation of a certain part of the circuitry. And because of that, there are a variety of outcomes. The functionality could be changed. It could be changed fairly selectively to sabotage a particular function of the circuit. It could be just for the purpose of defeating security measures or creating pathways for information leakage. Or it could be, in the case of process reliability Trojans, for causing early or premature failure of the device. So, as a result of that, we can see that there are a lot of different opportunities for introducing these kinds of vulnerabilities. The modifications could be introduced at, the design or the layout stage. They could occur anywhere within the supply chain. And as we've seen, the supply chain is fairly complex. It's stretched out, global. There are untrusted parties throughout the supply chain. And therefore, there are multiple avenues for these kinds of threats to be introduced. For this type of threat to be successful, it needs to be able to pass the typical testing that's performed on these devices. So functional testing that would normally be performed may not and typically won't catch it if it's done well. And we have to recognize that our adversaries in this regard can be very sophisticated. These may not just be parties that are interested in some quick financial gain, using shortcuts to produce something that can be passed off quickly as a legitimate device. They may be nation states, and their motivation might be, quite substantial in the sense of security threats and cyber warfare and, military goals. So there have to be tools that are capable of addressing these types of sophisticated threats. The ways in which these threats can be introduced, of course, are varied. The packaging itself, in the case of a clone device, will mimic and can mimic quite effectively an authentic device. Obviously, a circuitry can be modified. There could be new circuits. There can be additional interconnections or missing interconnections. They could be modified interconnections, and selectively added transistors that could be used to function as a kill switch to trigger a shutdown of the device at a critical time. So, what we have is many different avenues for introducing these kinds of modifications. And one of the particularly challenging or nefarious approaches that have been discussed in recent years and are concern are process reliability Trojans. As I mentioned a few moments ago, this would be a type of hardware Trojan where perhaps during processing, some subtle changes are made to materials or to dimensions such that the functionality of the device is retained, but wear out mechanisms are accelerated, and therefore the lifetime of the device is reduced. So, typically when a device is designed and then a fabricator is expected to produce that, we have a certain level of trust that the device will be laid out and produced in the form that it was originally designed as. And even when that nominal layout is in keeping with the design, these kinds of more subtle changes can cause a reduction in lifetime by activating mechanisms that I'll talk about in a moment to shift the lifetime distribution, for example, of the device in a way that's represented here, where a malicious modification brings some overlap in the occurrence of wear-out mechanisms down into the useful lifetime of the device. And looking at these a little bit more carefully and with the acknowledgement to the some of the sources from the literature from which this information is taken at the bottom of my slide, you can see a couple of the kinds of mechanisms that can be triggered to occur early as a result of the kinds of parametric changes in processing that are indicated here. Things like gate dimensions, gate oxide thickness, doping levels, the kinds of things that are buried quite deep within a device and require fairly sophisticated and targeted detection methods in order to uncover. Now, we heard also this morning from several of the panelists about zero trust and about the challenges in trust within the supply chain. So this is a concept, I think, that is very useful to keep in mind with respect to these kinds of threats, because so much of the processing and packaging of microelectronic devices is done by parties that are outside of a trusted supply chain. It's really helpful to use an approach where we start out with the assumption that the supply chain does not offer us a trust, and use methods for authentication and verification that ensure that what we're working with and what we're implementing in sensitive systems and products is in fact what we expect it to be. So adopting this zero trust concept from the network architectural domain to that of hardware and microelectronics is very useful in addressing these kinds of threats. And for that purpose, what we need is we need tools for detection, and not just knowledge that there's a problem, but ideally awareness of the nature of that problem in order to target our response to it effectively. So as we heard from Nader just a moment ago, I think he made a point very similar to the one that I'm making here. There are a couple different approaches one can use. And he was addressing specifically the hardware security kind of problem, but more generally with application to counterfeit detection of conventional as well as tampered sort. We have really two general approaches. One is when we have a known authentic device, which is referred to within some circles as an exemplar, then we can make a direct comparison in terms of any number of features, including second order effects, but also layout, materials, functionality, and so forth. In the absence of a device that we know to be authentic and trusted, then we have to be a little bit more creative. And we may have access to known IP, in which case that can be used as the basis for comparison of unknown devices or untrusted devices. And that known IP may come from the design, or it may come from a later part of the supply chain through which a level of trust extends. We can also look for consistency within a lot. Sometimes the counterfeit parts will be mixed in with a lot of good parts, authentic parts, in order to make it even more difficult to detect them. It's not always the case that 100% of the parts will be tested. That tends to be fairly challenging and costly. And so looking for consistency within a lot that's expected to be homogeneous is another strategy that one can use. And of course, the detection of vulnerabilities where we don't expect those is also another strategy that can be used. So I'll mention briefly again AS6171, which is a test method standard that has been developed for the purpose of providing industry with techniques for the detection of counterfeit parts. And this is in fact a workmanship standard. So it is one which is directed to ensuring consistency in the way that testing is done, reproducibility across different test laboratories, and also it was designed with the idea that the testing should be tailored to the level of risk and tolerance for failure or for security compromises that exist within the application and specific to the part. And this risk-based approach is one that is really central to the Department of Defense's strategy for addressing security threats of this sort. Back in 2016, the DoD issued the DFARS, which called for risk-based policies for addressing counterfeits. And further, and this was when it was ultimately issued, but in fact, the DFARS risk-based approach originated quite a number of years earlier. And in 2013, clarification of that explained in the DoD instruction 4140.67 explained that the purpose is to balance the risk represented by counterfeit goods against the impact on readiness and cost. So AS6171 was really developed to provide quantitative risk-based practices to meet this need and really to meet the need of industry to target the appropriate level of resources to the threat. And the G19A committee within SAE is the committee that's responsible for the AS6171 family of standards. So the quantification of that comes through the identification of defects, which are indicators that a part may be counterfeit or otherwise compromised. And these include features such as those that I illustrate here. They may be structural, material composition. They could have to do with electrical performance, really a wide array in different categories of indicators that something is not as we expect it to be. That includes documentation, for example, things of that sort.
Actually, I'll jump in with a question.
Yeah, certainly.
Here that came in. I think it's relevant here, but also a couple slides ago. So, how does the normal process variation lead to challenges to detecting malicious insertion tampering at the layout level?
Yeah. So that normal process variation is something that creates difficulties in identifying the modifications that might just be subtle and cause the perhaps premature degradation or aging, especially when it's as subtle as the illustration I gave you early when we're just looking at a tail of the distribution that's failing earlier. The challenge in detecting that is harder if we're just trying to do that testing at the beginning of life. So during the production phase or upon incoming inspection and acceptance testing, if we're doing some type of screening, at that stage of life, it's particularly challenging. What I will introduce in a little while is a strategy for doing real-time monitoring throughout the life of the device, which overcomes a lot of those kinds of problems where the normal modifications or variations within a population would make it nearly impossible to detect subtle changes like that in a one-time test that was done early in life. So hopefully I can address that question with what I'll be presenting in a few minutes here.
Okay. Another question I had, are there examples like that have happened where someone's hacked into a foundry and fiddled with process parameters? Has that happened?
I think that a lot of what we're addressing here is based on the knowledge that this is possible. But I think that specific knowledge of these kinds of events may reside on the other side of a security wall. And I think what we're trying to do is address a potential threat and not wait until it actually pops up in a widespread basis and affects us. So there very well may be specific incidents of this, but I couldn't say that I'm aware of those.
One other question came in here. It says, can the reliability Trojans be addressed by a burn-in test based on the individual failure mechanisms?
Yeah, so burn-in testing could address that. The problem with burn-in testing is, in order for it to be effective in detection of process reliability Trojans, it may end up being effectively destructive. I mean, you may end up consuming a significant amount of your useful life in order to trigger that type of Trojan. It's possible you could do that on a sampling basis, and you could simply use that as kind of an ongoing reliability monitor to detect populations of parts that have reduced life. And in that sense, it could be effective regardless of whether the reduced life is due to malicious tampering or simply due to process variation. So burn-in may very well have a role to play in this, but it may be one that comes at a cost in the sense that you may be consuming a significant amount of life that way.
Okay, thanks. I'll let you carry on here.
Okay. So as I mentioned a moment ago, there are a number of defects that have been defined as associated with what I would call conventional counterfeits. Within AS6171, there are 69 of those. In an effort to add tampered parts to the scope of AS6171, the subgroup that's been focused on tampered devices has come up with an additional 10 new defects that are more or less specific to this type of hardware security threat. And I list those over here. And I'm not going to go into them right now in detail because of time. But certainly anyone who's interested in this subject, I would really encourage you to contact me offline and to get involved in the effort within the G19A focused on detection of tampered parts. We could certainly use more subject matter experts and interested parties, so you're certainly welcome to participate in this effort. One of those that I will focus on from that previous list is unexpected emissions. And this gets into the topic that Nader talked about a moment ago, where we use side channel effects or side channel methods as one way of detecting modifications to a circuit or to a device. And there are plenty of examples of this. I show here a number of different kinds of emissions or signatures that one could detect. Electromagnetic radiation of various sorts conducted or emitted, magnetic characteristics, power behavior, thermal characteristics. Some of these have been demonstrated to be quite effective means for circumventing security measures, but they can also be used as detection techniques. And in fact, that is a very active area of development in detection. The existing methods within 6171 that don't go into side channel are also fairly comprehensive. So you can see what's already published here within that 6171 family of standards. that could provide some indication. But as I said, these have not been really targeted towards detection of tampering, but depending on the level of sophistication, they could reveal cloned devices, or they could reveal modifications to functionality. As certainly as we get down to the more destructive methods, where we're talking about decapsulation and delitting, and then of course design recovery, which is the reverse engineering that we heard about earlier. These are methods that could be used fairly effectively to detect tampering. And in fact, that particular document is undergoing revision now to make it more focused on detection of tampered devices. But many of these are perhaps incidental to tampering, and tampering may evade them. And so we are certainly working on more targeted methods, including Netlist Assurance, which Nader also talked about netlists, recovering netlists through design recovery or obtaining a trusted netlist, and then using that to compare to a device that was under test. And as I mentioned, design recovery, which is undergoing revision. And then there are other methods that certainly are under consideration for future incorporation in standards and development. And in particular, some of those side channel methods that I talked about. With regards to Netlist Assurance, this is going to appear as one of the slash sheets that similar to those I listed earlier. This would be /16 that would focus on the Netlist Assurance. And there are a number of approaches that are being incorporated into that standard as it's being developed now. So with respect to design recovery, in the interest of time, I won't go into this in detail. It's the recovery of not just the physical layout, but also potentially functionality and netlist information based on reverse engineering processes that are applied to a device. And of course, the tools that can be incorporated into this process can be quite sophisticated. So certainly, optical and electron microscopy and energy dispersive spectroscopy, but also, more sophisticated methods like secondary ion mass spectroscopy or, focused ion beam methods and things of that sort that could be used to recover the kind of information that could actually indicate modifications to fabrication process. And on the subject of second order effects, so here I give some examples where a number of organizations have developed methods based on power consumption analysis. And some of these employ machine learning for detection of anomalies or to make comparisons between groups of parts, for example, those that are known to be authentic and those that are not. So I list here several different methods that have been developed and published or commercialized by these organizations. And then also there is certainly commercialization of approaches that are based on electromagnetic radiation, such as the ADEC system from Nokomis. So these do exist and have been developed to a fairly significant extent. With regards to process reliability Trojans, there, of course, we have a greater challenge because of what we were just discussing in the Q&A and what I've mentioned earlier. There are some strategies that have been introduced, but it becomes difficult because of the complexity of microelectronics and the fact that these kinds of modifications could be buried quite deeply within a circuit, and as I said, could be quite subtle. So CALS's approach to this has been to use methods that are analogous to the digital twin concept, where we have a model of how a circuit should function and what a circuit's output or observable functionality would look like under a variety of scenarios based on a very detailed model of that circuit. And then the training of deep learning algorithms to recognize the various cases of alteration to that expected functionality through a fairly extensive training process that can be done virtually and essentially generate a library of what different kinds of behavior look like and how they would express themselves, not in very localized measures or features within a circuit, but in the externally observable characteristics of the circuit. So in this way, we can avoid having to overload our circuitry with localized and specific sensors embedded within the circuit. And we can do this on an ongoing basis, even while the device is being used in the field. And so by analogy to the well-known concept of prognostics and health monitoring, we refer to this approach as prognostics and security health monitoring, which can be used not just for detection, but also specific diagnosis and even prognosis. So I'll give you some insight into
a couple of questions.
Did we have a question, Jeff? Yes.
Yeah, I think you've addressed at least a bit here. The first one, how do you train your model in machine learning applications to the reliability Trojans? And the other question is the machine learning model using neural networks?
Yeah. So it is using neural networks. When we talk about deep learning, this is a deep neural network, which is being used. And yeah, the training process involves having a model of the system, in this case, the circuit, and then making modifications to that to mimic the various kinds of alteration that one would want to detect. And so that is a fairly extensive training effort. And so upfront, you have to invest a lot of effort in doing that. But you do that in a virtual sense, not in a real sense. Of course, you have to validate your model. And so it's essential that your models have good fidelity to the system of interest. But obviously, because of the complexity of the circuitry, we can have many possible classes of degradation. And that's represented in this chart at the top here. This is a 2D representation of a highly multidimensional phenomenon. But the colors serve to give an idea of all the different classes that one would want to detect, where each color represents a different kind of modification, or you might say a different mode of accelerated aging. And through a comprehensive program of training the deep neural network with the simulations that employ specific kinds of degradation that are implemented into those models of the system, one can recognize what that response would look like as an output of that circuit. And therefore, looking for these kinds of subtle changes in a fairly analog fashion, one can detect and distinguish or classify the various types of threat. And as a result, it's not just a detection of an anomaly, but it's a diagnosis of the nature of the problem as well. And once the detection has occurred, and then that anomaly has been classified into one of these many different classes, then one can also track it, because now this is not something that's being done at the beginning of life. This is actually being done in real time with the system in its usage environment. And one can see how the extent or severity of the modification and the detected functionality changes with time. And in doing so, one can do prognostics as well to predict when that system would fail, allowing the response to be, you might say, appropriate to not just the nature of the threat, but also the proximity of that failure. So the concept here is actually to incorporate this kind of monitoring into the circuitry because the overhead associated with it would be reasonably small, given the fact that a lot of the work is being done up front in generating the models and creating the means to do the classification based on more or less global functionality rather than localized features. And so this has obvious advantages in terms of identifying a variety of different kinds of hardware threats, as well as a variety of reliability and quality issues that might be associated with microelectronics, and doing that in real time and enabling a proportional response to the nature of the threat. So
maybe a couple more questions. I'll jump in here.
Certainly, Jeff.
It says, will the machine learning model allow you to identify the failure mechanism accelerated by the Trojan?
Yeah, that would. So you would essentially be simulating those various mechanisms in the way you train your machine learning model. And having trained it that way, then when the actual mechanism is active, you would recognize the way that it behaves according to the way that the models were trained.
And was that the color coding on that graph sort of indicated the type of?
Yeah, the color coding is meant to represent what that would look like. That you have a lot of competing mechanisms. You can think of each one of those as a particular kind of mechanism perhaps operating on a different part of the circuit. So in some sense, several of these colors might represent the same mechanism, but operating on different parts of that circuit. So there's certainly a lot of complexity to it. And the fact that they're mixed together makes that classification process challenging. But that's where the deep learning approach can be very powerful in looking at this multidimensional classification process and allowing you to separate out things that look nominally quite similar to each other.
Okay, and the other one that came in, I think you were maybe going to address that shortly. What are the challenges in the PSHM method?
Yeah, well, there are some challenges in having models that have high fidelity to real systems, to real circuits, real devices, and the training process. There are some fairly sophisticated statistical tools that we use at CALS to enable us to manage the extraordinarily high number of different conditions that have to be included in that training process in order for the model to work. And as you increase the different classes, and each class has different levels of severity, in order to train your model to recognize those, if you're not careful about how you approach that can blow up on you very quickly. And so there are some very powerful tools that are employed in order to make that a manageable process. And then, of course, this is something that requires the dedication of some resources in design and in sustainment and support of these devices. This has to be monitored. There have to be allocation of a certain amount of real estate and capabilities dedicated to this. But as I said, the idea is that there can be significant advantages, not only for, you might say, military and aerospace, but even for devices that are going into applications that are not very risk tolerant in other applications. Any other questions right now? I'll just kind of a couple slides away from finishing up. But did you have anything else, Jeff? Not right now?
No, not at the moment.
Okay, great. Yeah, so I'll just talk briefly about, where I see things going and where the needs are. So certainly there are some pretty effective standards-based methods that exist right now. And from my position as chair of the G19A committee within SAE, I would like very much to see more consistent and broad adoption of the standards for counterfeit detection as a whole in government and industry. And I see that happening, but it does seem to be taking some time for organizations to recognize the power and the value of what's been created already. And then, of course, the involvement in the ongoing effort to strengthen these standards-based methods to target areas of current concern, such as the hardware security threats that I've been talking about, the more sophisticated modes of counterfeiting involving clones and those that are being carried out by more sophisticated actors. In addition, there's a need for objective data. The data that is being used to support the various test methods and to quantify their appropriateness for different levels of risk is still not extensive. Fortunately, DoD did recently engage with CALS to generate some more of that data, and this is a very recent development. So I'll just describe that very briefly in a moment. And then, of course, as I mentioned, just the pure detection process is just the first step. And I think that given the nature of the kinds of threats we face, there's a real need for diagnostic and prognostic tools that can be used not just at time zero in the laboratory or in the test facility or in a production facility, but really in the end-use application, because it's very difficult to anticipate every possible threat and to detect that at the beginning of life. So I'll just mention briefly recent work that CALS did for the Defense Microelectronics activity under the 2019 NDAA, which was a review of existing and emerging counterfeit detection methods. And that included a blind study of various methods with known real counterfeits, including clones, as well as more conventional types of counterfeit parts. And also as a part of that, there was a portion of that review was really focused on the legislation, the policies, the standards, and the kind of internal requirements that are needed within DoD for the organization as a whole to be more effective in countering these threats. That part of it was led by the University of Maryland School of Law. And so what CALS did in the blind study, as well as in the evaluation of the technology readiness of various methods, was to work with a number of organizations, commercial organizations, and I'll show you the list of those here in a moment. And after conducting the study, provided recommendations for both long and short-term policy and practice changes within DoD. So you see here on the right, the organizations that were involved in sort of putting together the study: CALS, DMEA, and SMT Corp, which had the inventory of known counterfeit parts that was so effective in making this study an objective evaluation of different methods. And then there were different categories of detection methods that fell into machine vision, side channel, and then conventional standards-based techniques. And the organizations that were involved in each of these are listed here. So, certainly what we found was that there were techniques in each of the three categories that exceeded 99% accuracy for a number of different kinds of known counterfeits. But in terms of technology readiness, there were challenges in the machine vision and the side channel categories that require some more work in terms of making them suitable for the wide range of application environments for which they would be needed to be deployed by DoD in order to be effective. But certainly there's great promise there, and there's also a need for a real dedication to the implementation of the conventional standards-based methods that are currently available and extremely effective, as we found. So with that, I will end my talk, and I do want to acknowledge the contributions of the faculty and staff and students at CALS, the G19A committee, and I really appreciate the questions I received already, and will be happy to answer any more that we might have time for.
Great, thanks, Michael. Actually, a couple more have come in. It seems like the machine learning has piqued some interest here. One, so it seems like supervised learning is used. What are the considerations about using unsupervised learning to train the model?
Yeah, so unsupervised learning is really valuable for anomaly detection, and one can identify behaviors which are, you might say, sparse or infrequently occurring through unsupervised learning, and potentially those could represent anomalous or undesirable characteristics, and so those could be flagged. But because it's unsupervised, you don't have the labels to diagnose the nature of the problem. And it's also not always easy to know that the characteristics that you're looking at are going to cluster themselves in a way that I described that makes it easy to distinguish the undesirable from the desirable behaviors, because there's such a wide range of usage conditions and characteristics that themselves may be infrequently occurring. And so just this kind of unsupervised clustering-based approach can be imperfect, but it can be powerful in the sense that you don't need to know a whole lot ahead of time in order to do something to detect a problem. So I think it has a place within our toolbox, but it's limited in the sense that it's not going to tell you what's wrong. It's just going to tell you that you should look for a problem, potentially.
And the issue of known versus unknown unknowns.
Right.
Plays in there. Another one here, this person says, I might have missed it. It appears in a deep learning model, there would be no way to differentiate whether you are capturing aging due to process variation versus intentionally introduced during manufacturing. I think you
so, in one sense, you could say it almost doesn't matter, because if you are, depending on the availability of a device or a circuit for functionality within an application over a period of time, and what you detect with this PSHM approach is that your remaining useful life is going to be cut short, right? Regardless of what the underlying cause, you really need to address that, because you are not going to have availability when you need it. Now, you may be able to distinguish that from normal process variation simply in the sense that you might have, some expectation based on qualification and reliability data that the useful life of that device is typically 80 years, and here you are after a year and a half having to replace the device. That seems like, there's something wrong there, right? It could be a mishap within the process. It could be deliberate. But ultimately, the ability to diagnose and predict when that device will cease to be available to you is really what's essential in ensuring the continued success of that application.
Thanks. One question I had, that CALS DMEA work, is there a published report or summary or something of that?
Yeah, I wish I could say that it was published, but DMEA has undergone a number of organizational and administrative changes over the last few months, and those happened just as we issued our report to them. And so we're just waiting right now, waiting for permission to release portions of the report and to publish it and to make it more widely available. So I really anticipate that that's going to happen. We've certainly heard from DMEA that it's their intention that, certainly portions of this work should be disseminated through conferences and publications, and they're anxious to do that. but we're just in a waiting pattern right now, in a holding pattern.
Okay, understood. Okay, well, thanks. That's all the questions in the window here. So thank you, Dr. Azarian.
And once again, I would like to thank our sponsors, Omcore Technology and Advantest, who made these presentations and this workshop possible. So thank you, Omcore and Advantest. Omcore has multiple differentiators as a leading OSAT in areas of technology, quality, and services. And Advantest is voted the best ATE company in 2020 based upon the VLSI research rankings with high rankings in multiple categories. So congratulations to Advantest. So I'd like to thank them as sponsors. And I would like to once again thank you for attending and look forward to seeing everybody here again tomorrow, and have a good rest of your day. Thank you.